Hello, this is Trude Socrates, and I welcome you to a portrait of linear algebra. So in our last video, we introduced the concept of an abstract vector space. So we decided that the 10 properties which appeared in the main theorem of section 1.1 will be turned into axioms that we require a vector space to possess. So in this video, we are going to extend the ideas that we saw in chapter 1 and construct linear combinations, spans, and test for linear independence in these abstract vector spaces. So those are our goals for this video. So the definition of a linear combination for an abstract vector space is essentially the same as that which we saw in chapter 1. So let's suppose that V1 through Vn, which make up our set S, is a set of vectors from some vector space V under this addition and scalar multiplication. And suppose that C1 through Cn are real numbers. So a linear combination of these vectors, V1 through Vn, with coefficients C1 through Cn, is an expression of the form C1 times V1 plus C2 times V2 all the way up to Cn times Vn. So we saw this definition in chapter 1, and it's essentially the same, except for this weird scalar product and this weird vector sum. So of course we're going to get rid of those a little bit later. So similarly, the span of the set of vectors is the set of all positives of these vectors. So of course, the simplified notation will just be C1 times V1 plus C2 times V2, all the way up to Cn times Vn. All right, so in our last video, we introduced the vector spaces, which we called Pn. And they were all polynomials whose degree is at most n. Okay, so I bring this up because I actually chose this example because a linear combination is already hiding in this expression. Okay, because we had C1 V1 plus C2 V2. Okay, so let's start at the end over here with the highest power. So obviously we can think of the monomial x to the n as multiplied to c sub n. Okay, and we can work our way down. So think of x squared as being multiplied to c2. Okay, and as promised, we're not going to put these silly circles around our times and our plus. Okay, so think of this as x times c1. Okay, what about c0? Okay, there's nothing besides c0. Oh, except it's kind of hiding. We can think of c0 as c0 times 1. Okay, the constant 1. So this becomes a linear combination of the set of monomials. Okay, so the monomials 1, x, x squared, and so on, up to x to the n. Okay, so I want to point out to you, how many monomials do you see here? Okay, you might say n, but no, not quite, because that's x to the 1, x to the 2. And so you can also think of 1, in all honesty, as x to the power 0. Okay, so that is x to the 1, 0, 1, 2, up to n. There are n plus 1 monomials in this set S. Okay, so we can also say, we can thus conclude that we can write Pn as the span of this set S. All right, we're going to keep working on our polynomial spaces, but now we're going to talk about membership in a span. And I hope that that sounds familiar. We saw it in section 1.5 when we talked about the Gauss-Jordan algorithm. Okay, so the question is the same, essentially. We called it B in section 1.5. Let's call it W this time. Is a vector W in the span of S, where S is a finite set of vectors from V, and W is another vector from V. Okay, so our playground is V, and we have a set of vectors in V. We look at their span, all possible linear combinations, and we ask, is another random vector in V, that would be W, part of this span, a member of this span? All right, so if we stay in PM, we can use this following rather powerful theorem, although it almost looks obvious. Okay, so it talks about the equality of polynomials. Suppose that P of x is the linear combination C0 plus C1x through Cnx to the n, and Q of x is D0 plus D1x through Dn x to the n. So we need a different letter for that linear combination. Then as functions, P of x is exactly equal to Q of x if and only if the coefficients are all pairwise exactly the same. Okay, and you might say that's obvious. Okay, how can one polynomial be equal to another polynomial unless all the coefficients are equal to each other? It's actually not that obvious. Okay, we will need what is called the fundamental theorem of algebra in order to prove this theorem. Okay, so consequently, if we want P of x to be the zero polynomial z of x, so remember that z of x, all the coefficients are zero. It's 0 plus 0x plus 0x squared all the way through 0x to the n. Okay, so this theorem says that this polynomial is a zero polynomial if and only if all the coefficients are equal to 0. And again, that kind of sounds obvious, but no, actually it's not. All right, so let me just clarify what does it mean for two polynomials to be equal as functions. Okay, so what it means is that the values of those two polynomials are exactly the same for the same input, a real number. Okay, so in other words, if you plug in 5 to both polynomials, you should get the same answer. P of 5 should be the same as Q of 5. P of negative 3 should be the same as Q of negative 3. Okay? All right. Another way of saying that, of course, is that their graphs are exactly the same. Okay? If you draw their graphs side by side, they will look exactly the same. If you draw them in the same Cartesian coordinate system, they will overlap each other. Okay? So let's use this theorem in order to decide if this polynomial, P of x, is a member of the span of this set of vectors. Okay, so let's look. That's x cubed, x squared, x cubed. So the highest power is 3. All of those polynomials are in P3, and this is also in P3. Okay, so we want to know, is this P of x part of the span of this set of vectors? And if so, how can we express this polynomial as a linear combination of these polynomials in S in the simplest way possible? Okay, so I hope that sounds familiar to you. Okay, essentially the same question back in section 1.5. So what is the simplest way that we can express B as a linear combination of our vectors in S? Okay, so the question now becomes, can we write P of x as a linear combination of these polynomials? 1, 2, 3 polynomials. So the question is, can we write C1, first coefficient, times first polynomial, plus C2 times the second polynomial over here, plus C3 times the third polynomial equals P of X. So let's copy this whole. All right. So that is the equation that we want to solve for C1, C2, C3, if possible. Okay. So what are we going to do? Well, we can simplify the left side by distributing C1, C2, and C3 to those three polynomials. Okay, so here's what I'm going to do. Let me focus on the constant terms first. Okay, so we get minus 6C1 plus 2C2 minus 4C3 right there. Okay, now let's focus on the terms with X in it. So we have minus 3C1 plus 7C2 plus 13C3. Okay, see what's happening? So next, I should put an X over here. How about X squared? Okay, so there's no X squared over here. There's a minus 2 times C2 and a minus 5 times C3 for X squared. Okay, last term, we need X cubed. So what have we got? 4C1, no X cubed from C2, but there is a 6C3. Okay, so we want that equal to this polynomial. So I'm not going to write P of X this time. Okay, the theorem that we just saw said that this linear combination will be exactly equal to this linear combination as functions, if and only if these coefficients are pairwise the same. So thus, we must satisfy the, how many equations? 4 equations. What are those 4 equations? This coefficient must be equal to -4. Next coefficient, this must be equal to -5. Next, this coefficient must be equal to 1x squared. And, just enough space, this coefficient must be equal to 2. Okay, so we have to satisfy these 4 equations. C1, C2, and C3 have to satisfy these 4 equations. Do those look familiar? But of course, that's exactly a system of linear equations. How many equations? 4 equations in 3 unknowns. Okay, so you remember your adjectives? Is this an underdetermined or an overdetermined system? Okay, I believe it is an overdetermined system. Okay, so our next goal, of course, is to solve this. All right, but of course, we did all that work in chapter 1. Let's turn this into a matrix. Okay, so our variables will be C1, C2, C3. Okay, and let's look at the coefficients. We have minus 6C1, minus 3C1, no C1 in the third equation, 4C1 in the last one. C2, we got 2, we got 7, we get the minus 2, and no C2 in the third equation, in the last equation. Okay, C3, negative 4C3, 13C3, negative 5C3, and 6C3. C3. Okay, so the right side, minus 4, minus 5, 1, and 2. Okay, so we have that system of equations. We want the area. Compute matrices RRE. Ooh, okay. So you remember your consistency test or inconsistency test? Zeros, zeros. So we don't see 0 equal to 1. Okay, so this system is consistent. Okay, so as usual, we can look for all the solutions. Okay, so how will we write it? Like C1 plus 3 halves C3 equals 1 half, and so on. Okay, but we were being asked, okay, what is the simplest way to write p of x as this linear combination, if possible? Okay, so yes, it is possible because the system is consistent. So our simplest solution will be C1 equals, looks like it should be 1 half, and C2 must be negative 1 half. And guess what? We still need a C3. C3 has to be 0. Okay, so this would be the simplest linear combination. And again, we said that yes, it's part of the span. This p of x is part of the span. So we can check. Okay, C1 is 1 half. Yeah, there it is. C2 is negative 1 half. Minus 1 half. Okay. I am going to just replace C3 with 0 because I'm going to do one more thing after this. Okay. So do we get this as our linear combination once the dust settles? Ooh, okay. So Maple has this funny thing of, well, maybe not so funny, of arranging the terms in decreasing order, because that's usually how we teach it in basic algebra, right? So there's 2x cubed, x squared, minus 5x. It works. Okay, so yes, this p of x is part of the span. Okay, so what is I going to do? Well, what if we change p of x? So let's give it meaning. So instead of minus 4, let's start it off as minus 3. Okay. Will this still be in the span? All right, so just change minus 4 to minus 3, minus 4 to minus 3. Everything else is the same, right? It's only the right side which is the same. Okay, and let me save this. I'll just put that on the next slide. Compute matrices. Area. Ooh, pass or fail. Ooh, okay. That's bad news. Okay, so this is inconsistent. And so Q of x is not in the span. Shall we put it on the next line? Not in the span. Okay, so yeah, I kind of mentioned this before. Okay, systems of linear equations are very sensitive. Okay, make one little change on the right side or maybe on the left side, and yeah, it doesn't work anymore. Yeah, you want to change something on the left side? Okay, let's bring back negative 4. Okay, if we change one of these, will it still be in the span? What if we turn the 4 into a 3? Let's see. Okay, matrices. Alright. Ooh, it is still in the span. We don't see 0 equals 1. But hold on. What makes this different now? Okay. So this was our original REF. And yeah, we get our simplest solution right here. Okay. This one has no solutions. This one, C1 is now 0. C2 is -4/3, and C3 is 1/3. Okay, so big difference. In the first one, we have a free variable. Now we don't have a free variable. Okay, so more on that in just a little. Ta-da! Of course, those free variables should remind you of the time when we talked about linearly independent or dependent sets of vectors. Aha! So, very similar definition. Again, only the notation is different. So let S, V1 through Vn, be a set of vectors from V. We say that S is linearly independent if the only solution to the equation, which is again called the dependence test equation, C1 V1 plus C2 V3, V2 all the way to Cn Vn is the zero vector, is the trivial solution where all the coefficients C1 through Cn have to be 0. Okay, we abbreviate it as just being independent. The opposite of being independent is again being linearly dependent. So this means that there is a non-trivial solution to the dependence test equation, a solution where at least one of the coefficients is not 0. Okay, so we are going to keep working on polynomials and also with more general functions. Okay, and since polynomials are functions, let's talk about it for a set of functions, f1 through fn, from the space of functions which are defined on an interval I. Okay, so we say that S is linearly independent if the only solution to this test equation, C1f1 all the way up to Cnfn, is the zero function. And this much must be true for all x in the interval. And the only solution must be all the coefficients equal to 0. Okay, so what I want to warn you about is that it may be possible to satisfy this equation for some of the input numbers in the interval I. Okay, but that's not enough. You must satisfy this equation no matter which x you plug into the left side of the equation. The right side is always going to be 0. Okay, so you have to keep that in mind. All right, so let's bring back the set S from our last example, and we'll decide if S is dependent or independent. Okay. Okay, so here are the original polynomials from that example. Remember, we changed p of x, but we don't have to worry about that because the right side of our equation is now the zero polynomial. Okay, so this is our test equation, and yeah, this was the original coefficient in that example. Okay, so what's going to happen is that the left side of the equation, of course, simplifies to exactly the same thing, but this time you want it to be the zero polynomial, so every coefficient has to be 0. So I hope this reminds you that all this is a homogeneous system of equations. Do we really need the zeros? No, of course not. But let's put them anyway. Okay? So find the REF. Compute matrices REF. And yeah, it's kind of anticlimactic because we saw that left side in the previous example. Okay? So Yes, there is a free variable, so therefore this set of vectors is dependent. Since there is a non-trivial solution, S is dependent. Okay? So, of course, the obvious follow-up question is, find the simplest dependence equation. Okay? So what is the simplest way by which we can create the zero polynomial out of these three polynomials? Okay? So, again, does that remind you of something? Yeah, it's just a null space, right? So make x3, or c3 in this case, my apologies, to be 1, not 0, and then solve for c1 and c2. Okay? So therefore, c1 will be negative 3 halves. Let's just do it there. So multiply the first polynomial by negative 3 halves, the second by negative 5 halves. So let me copy this here. Negative 5 halves, and C3 is just 1. Okay, so we can get rid of that C3. Will we get the zero polynomial? And, oh, yes, of course. Now, Maple does not know who z of x is. Okay, for Maple, the zero polynomial is just represented as the number 0. Okay, even though, yeah, now that you've seen it, that does look confusing, right? How can a polynomial be equal to 0? But actually, of course, we've been dealing with it that way since basic algebra. Okay, so as a bonus, let us look at that set where we changed the last coefficient in the first polynomial into 3. So the 4 just turns into a 3. Okay, so do we get a free variable? Interest rates are yet. Ooh, look at that. So yeah, we had the solutions last time over here because we were solving for p of x. Okay, but this time the right side is all zeros, so we do not get a free variable. C1 has to be 0, C2 has to be 0, C3 has to be 0. Okay, so therefore this S prime, where we change that coefficient, is now dependent. I'm sorry, who? Is now independent. Okay. Okay, let's do a quick example from trigonometry. Okay, so these three functions are defined for all real numbers. So they're from f minus infinity to infinity. Is this set dependent or independent? Okay, so is there a linear combination of these three functions? They're not polynomials anymore, which is 0 no matter what x you plug into it. Okay, so cosine 2x. I hope that looks familiar to you. So your brain is obviously thinking of the formula for cosine of 2x. Okay, and are these part of that formula? Yeah, of course. So cosine 2x is, of course, cosine squared. Plus or minus? Minus, because if it were plus, it would just be 1 all the time. That's the formula for cosine 2x. So, how can we rewrite this so that we get a linear combination of these three functions? Okay, so we can write that as cosine 2x plus sine squared x, our second term, and then minus cosine squared x, our third function. Okay, so that's simply 1 times the first function, plus another 1 times the second function, plus, I can write it this way, negative 1 times the third function. Okay, so that will add up to the 0 function because of this identity. No matter what x you plug into this equation, you will always get the number 0. So therefore, this set is, which one? No mistakes this time. This set is dependent, not independent. Okay, so let's make some generalizations about small sets of vectors. You saw these essentially in chapter 1. Okay, so if you have a single vector in your set, when is that going to be independent? Well, you'd better not have 0 vector. Okay, so remember in chapter 1, the set consisting only of 0n is dependent, but if your set does not contain a 0 vector, then it is independent. It follows from the zero factors theorem, which we proved in general in 4.1, our last video. When is a set of 2 vectors independent? When they are not parallel to each other. So again, that should sound familiar. What we did just now with cosine 2x and cosine squared and sine squared, that's a demonstration of this more general statement. Suppose now you have several, 3 or more, vectors from a vector space. That set is dependent if and only if at least one of those vectors, and without loss of generality, you can pick the first vector, is a linear combination of the other vectors of S. Okay, so we express cosine 2x as cosine squared minus sine squared. Okay, so the first function is a combination of the other 2 functions. Okay, so in general, we want the first vector to be a linear combination of the second, the third, all the way up to the nth vector. All right, so let's go back to polynomials, but this time we are from P4, okay? And there is something very special going on about this set of polynomials, okay? So, same question. Is this set dependent or independent, okay? So, we want C1 times the first polynomial plus C2 times second polynomial times this. And yeah, there you go. Looking for the comma over there. Plus C3 times the third. And there's the next comma. Plus C4 times the last, which is the 5. Okay? So we want to know, are there any non-trivial solutions to this dependence test equation? Okay, so we could do exactly what we did earlier. Okay, we can expand the left side and then compare coefficients. Okay, but let's do something a little bit smarter this time. Okay, what can we do? Well, so x to the 4th. Okay, wait a minute. There is no x to the 4th in the other 3 polynomials. Okay, so since x to the 4th appears only in the first polynomial, what has to happen? Well, there's a 0 x to the 4th here. So 2c1 has to be 0. Must be 0. And so c1 equals 0. That's the only possible solution. That's the only possible value for c1 if you want to satisfy this equation. Okay, but now that c1 is 0, this whole term is now going to disappear. So we can update the test equation. Okay, So now we have a shorter test equation. I hope this feels familiar, right? Okay. So let's keep going. I see an x cubed over here, but there is none over here and none over here. Okay, see what's going on? So therefore, this time, x cubed is by itself. And so 7c2 must be 0. Let's stop playing games. That should be c2 equals 0. Okay, see what's going on? Update now. c2 is 0. So that is our new test equation. X appears by itself in the third polynomial, which is now the first in that test equation. And so, again, we get C3 equals 0. Okay, so the final update, C4 times 5 must be the 0 polynomial. No, wait a minute. So thus, C4 equals 0 also. Okay, so I did say that this set of polynomials is kind of special. And yeah, this is a 4th degree polynomial. This is a 3rd degree polynomial. 1st degree, I didn't include a 2nd degree polynomial, but that's fine. And there's no x here, that's a 0 degree polynomial. Okay, so therefore, we can make this generalization. There you go. So if you have k polynomials, and they have distinct degrees, okay? So in particular, we can arrange them in decreasing powers, decreasing degrees, okay? Then that set of polynomials must be linearly independent, okay? What's the simplest set of polynomials? The set of monomials. 1x all the way up to x to the n, and we've gone full circle. This was involved in our first example. So therefore, the set of monomials is linearly independent. Okay, so that is our video for today. This is True Socrates signing off. I hope you enjoyed, and I will see you in our next video. So until then, may the force be with you. Bye.